We finished chapter 3 with 3 lessons. We're going to do one today, and then we'll do the other ones when we come back from Thanksgiving break. Today, we're going to, all of them have to do with growth and how things grow, or shrink, I guess. It could be negative growth. But we're going to focus on living things. When we come back from Thanksgiving break, we'll focus on money in particular and how money grows, because that grows differently than things that are alive. But today we're going to focus on things that are living. So when I talk about living things, I talk about population, right? So it could be people. It could be bacteria. It could be a virus. It could be animals. Okay, when we're talking about things that are alive, these are the kinds of things we're talking about, and there's a particular formula to use when you're talking about things that are alive. And it has to do with the letter E in it. Well, sometimes, not all the time. All right, so here you go. This is the formula for things that are growing, or we call negative growth, we call that decay. But this is the formula. P equals P sub O, so it's a little O subscript there, 1 plus or minus R, and the power is T divided by K. I will give you this formula, but I won't tell you what the things mean. Your job is to know what each part is, but I will give you the formula like that. You don't have to memorize it, but you need to know what all the parts are. All right, so let's start with what those things are. So P stands for the population. And the difference between P and P sub 0, or P sub O stands for the original size, or the original amount. So the regular P is like the population now. So maybe you want to add population now. And then P sub 0 or P sub O is the original or the initial, sometimes they call it initial, size or amount. One plus or minus R is what they call the growth factor, or it could be called the decay factor. If something is growing, then it's plus R. That means it's getting bigger. If something is decaying or declining or decreasing, then it's going to be 1 minus R. And so you just have to read into the question. If it says that it's growing or if it says it's shrinking, then you use either a plus or a minus depending on what the question would tell you. So just be careful you use the right amount. T is time. Time could be measured differently. It could be days, years, hours, seconds, minutes, months, anything that we use to measure time. Okay, K is what we call the frequency. And it'll say something like every blank days or something like that, or every 4 years, or every 6 months, or it's like the frequency, almost like a cycle, how often that's happening. Okay, it's like, my mom measures my height every year on my birthday, or my whatever, I take my pulse every day at this time. If it's every something or how often it happens, that's the frequency cycle, and that'll be going in for K. So that's what the numbers mean. And then your job is just to drop those numbers into the different values and be able to tell. All right, so let's practice with the numbers already being there. So here's an example of something you might need to look at, and then what could you tell with the numbers already there? Okay, San Jose and Detroit. I'm going to give you a population model for both. Okay, so San Jose, West Coast city in California, Detroit, Midwest city. All right, here are the population models for both. P equals 898,759 parentheses 1 .0064 T. And then Detroit 1,03368 and then 0.9858 T. All right. I literally could ask you to write me a paragraph story about San Jose or in Detroit just from those equations. I could say, what can you tell me about San Jose and Detroit just by looking at those two equations and how they're set up? And you should be able to kind of tell me a little bit of a narrative about these two different cities. Okay, so somebody tell me anything, something about these two cities you can tell by looking at those equations. Ben. Okay, San Jose is growing, Detroit is losing. How can you tell that? Okay, all right, very good. So something you can tell just by looking at these numbers. Okay, that is a number that is a 1 plus. It's 1 plus and then 0.0064 is more than 1. And so what Ben is recognizing is that that is a growth number, it's a growth factor. So San Jose is a city that is growing. And then what he's noticing here is that that must have been 1 minus. You had to have subtracted something to get that number. And so Detroit is a city that's in decline or decay. Okay, the population is going down. And if you know anything about those two cities, that should make sense. San Jose is, in a largely tech area, and so lots of growth happening in that industry. Detroit is an industrial area, the car manufacturing, and that city is really in its decline. And so you can tell that just by looking. Now, if I were to press Ben a little bit more and ask him a little bit more specifically, like what is the exact growth factor, he should be able to figure that out. So for example, for San Jose, 1 plus R is the number 1.0064 right now. So how could I figure out exactly what R is? Subtract 1, right? Minus 1 from both sides. And so the growth factor is 0.0064, which if you change that to decimal by moving the decimal place over, R is 0.64%. So San Jose is growing by 0.64%. Now Detroit, we could do the same thing. Detroit's 1 plus R is 0.9858, because remember 1 plus R is what's in the parentheses. And if we minus 1 to both sides for that, R is going to turn out to be a negative number. And that turns out to be negative 0.0142. And in percentage, that means negative 1.42%. So Detroit is declining. Okay, what's the frequency on this? How often is it declining? Can you tell me that by looking at the equation? Where would you be able to tell the frequency? Okay, let's look at this. What letter represents frequency? K, all right, so it's T divided by K. All right, so in my T, you're like, well, it isn't divided by K. I'll say, yes, it is. Okay, what's K, the K value? If there's no K there, then we understand that K is 1. And so the frequency cycle is every 1 year. This is happening every year. All right, so that's the frequency cycle, that this is happening every 1 year. And this is happening every 1 year. Okay, what else could you tell me about San Jose and Detroit? Anything else just from looking at the equations? Pedro. Okay, population now is the P. those other numbers aren't the population now. They're the population that's different, right? Population now is P. That's the one that's over here. These numbers are in the P sub 0. So what do those numbers represent? The original, okay, when they started counting this. And this, I didn't tell you that, but these numbers started keeping track in the year 2000. Okay, and so this was keeping track starting in the year 2000. And so the population back in the year 2000, when we originally started keeping track, that's these numbers right here. So this is in 2000. There were 898,000 people, and in Detroit in 2000 there were over 1 million people. But now, of course, we are 19 years, almost 20 years later from there, and so we could figure out, well, what's the population now 20 years later? Okay, so let's do that. Let's find the population when, let's do 2020 since we're so close to 2020. What are the populations now? And we're going to do t equals 20, which is going to be represent 2020. So it's 20 years later. So I would encourage you to use VARs on your calculator, which is why I had you get it out. All right, can you go ahead and get out your calculators and put those two, one into Y1 and one into Y2. And we'll find the populations of the two cities now. All right, so hopefully you have those two in. And so if we want to use the calculator to determine the populations now, I would say, okay, use your VARs. Y1 is where I put San Jose, and then I'm going to put 20 in for the amount of time. And so now San Jose is 1,021,071-ish people. And then use VARs 2 to look at Detroit, and Detroit should now have gone down. And Detroit is now 904,013 people. And so San Jose has now exceeded Detroit. There are more people now in San Jose than there used to be, and than there are in Detroit. So you're comparing the two. All right, let's keep going with these growth models. Okay, here's our next example. Okay, so example, write your own growth model. All right, A. P sub 0 equals 12, and R equals 8% every year. Okay, and so using our equation for our growth model, you're going to put those numbers in and be able to come up with a growth model. So your growth model should start P equals. So we know P sub 0, which is the original amount, is 12. In parentheses, we're going to put 1, and this is an 8% growth rate, so this is plus 0.08, so it's a positive growth rate, not negative. Every year means the cycle is 1, so T would be over 1 for K. Now you don't have to write over 1. You could just leave it as T, so your population model could really just be 12 parentheses 1.08. You can go ahead and add those together to the T. And that is your growth model to represent a population that starts with 12 of something and then grows at 8% per year. All right, here's another one. Okay, try if p sub 0 is 200. And it's going to be doubling every 12 hours. So you want to practice writing a growth model for that. Doubling every 12 hours. So P equals, P sub 0 starts with 200, 1 plus, now the doubling rate, that doesn't mean I add 2. That's not what it means to double. To double means you add 100%. Okay, to double something means you start with your full amount and you add 100% more, and now you have double what you had before. And so we add 100% to that. That's what doubling means. And then every 12 hours would be t divided by 12. Now 100%, we want to put that into decimal. So if we take off the percentage, where do we put the decimal point for 100%? Where will that decimal go? After the 1, right. 100% is 1.00. And so this will end up to be 200 times 1 plus 1, which is 2, t over 12. And that's the frequency, the cycle that it's happening. Okay, C. Let's say the original is 400 grams. And it is halving, okay, cutting itself in half every 5 days. So is this getting bigger or smaller? Smaller. And so when we set up our population model, the 400 would be the original, and this would be 1 minus. And you got to think of halving as a percentage. How much is half? 50%. So 1 minus 50%. And then every 5 days would be t over 5. So then you turn 50% into a decimal. The decimal for 50% is 0.5. And so our model becomes 400 times 1 minus 0.5, which is 0.5, to the t over 5. And that's your model. So a good chunk of your homework is practicing writing the models. Okay, once you have a model written, then you're going to need to solve some questions about it. Okay, here we go. You have, you start with 100 bacteria in one of those little petri dishes. Do they still do that in bio? Do you guys have those little round petri dishes and you grow awesome mold and stuff in there? Okay, so you have 100 bacteria in there. It's doubling every hour. Okay, so tell me, when will there be 350,000 bacteria? How long will it take? So first you want to write your model. P equals 100 bacteria. Doubling is 1 plus 100% growth. Every hour is t divided by 1. This is happening every single hour. So we know 1 plus 100% is 2. And then it's just to the t. We want to know when it's going to be equal to the population now, being 350,000. So where do I put 350,000? In for time. So 350,000 goes in for time. And now you're going to do legal math to both sides to solve for t. So what should I do first? Divide by how much? Divide by 100. Good. Okay, so divide by 100. That's going to give me 3,500. equals parentheses 2 to the t. And now we need to do a legal thing to both sides. Okay, this is where all your skills come into practice. What do we do to both sides legally here? What do we want to get rid of? The 2. 2 is a base. How do we get rid of a base? With a log. Okay, what log? I always recommend natural log. Okay, I recommend natural log. So use a natural log around the 3500 and use a natural log around the parentheses 2 to the t. Because then what can you do with the t? Move it to the front for sure. All right, so then we've got natural log 3500, and t is in front of natural log 2, which means I just have to divide natural log 2 on both sides. So we divide natural log 2. This is why I had you get your calculator out as well. So type in natural log of 3500 divided by natural log 2, and that will tell you how much time it will take for your bacteria to go from the 100 that you started with to the 350,000 that you ended up with. Who's got that answer? 11.7 what? Hours. Okay? So less than half a day for 100 bacteria to go to 350,000 bacteria. And it only takes one. Like you get a little cold virus thing, and that 12 hours later you could be sick because there's that many of them in your body. Okay? All right, here's one from chemistry. That was a biology one. Here's a chem one. We might not finish, that's okay. Okay, so if you have 5 grams and its half-life is 20 days. Okay, half-life is 20 days. All right, how does that work? How do you make a model for that? Okay, well, 5 grams is what I start with. Half-life is 1 minus 50%. That means you go down by 50%. 20 days is the time, or the cycle, so t divided by 20. And then half is 2.5 because we went down by 2.5.